What if I told you that 0 degrees Fahrenheit, the baseline we use every winter to figure out just how miserable it is outside, was actually based on a completely random bucket of salty ice water?
Right. Yeah, Daniel Fahrenheit
Mhm.
essentially just found the absolute coldest slush he could reliably recreate in his lab back in the 1700s.
He just jammed a thermometer in it and said, hey, this is 0.
Exactly. I mean, it was a completely arbitrary mixture of water, ice, and salt. And somehow, that exact mixture still governs a massive portion of modern engineering to this day.
It's honestly kind of mind-blowing. Welcome to the deep dive, by the way. We've got a really fascinating stack of source material sitting in front of us today.
We do.
Yeah.
We are looking at a highly detailed instructional manual created for skilled trades. Specifically, it's for instrument technicians.
Yeah, it's this incredibly thorough breakdown of the science of heat and temperature. And, our mission for you today is to pull back the curtain and demystify these invisible thermal forces that, quite frankly, dictate how reality behaves.
Right.
We're going to break down how a simple pot of water boils, but more importantly, we want to uncover the hidden engineering secrets behind things like bridges, industrial boilers, and even that little mechanical thermostat clicking on and off on your wall.
And our goal here is to skip the road memorization. We aren't going to just, throw a list of mathematical conversion formulas at you to memorize for some pop quiz.
Please no.
Right. We are looking for the why. We need to understand how the transfer of invisible energy literally reshapes the physical world around us.
Because mastering these concepts is really the only way to genuinely understand modern industrial processes or mechanical engineering, or even the climate phenomena happening right outside your window.
Absolutely.
Now, I know the phrase trades manual on thermodynamics sounds like something that would instantly put you to sleep.
Oh, for sure. It sounds incredibly dry.
Right. But here's where it gets really interesting. The manual actually maps out the secret personality, I guess you could call it, of everyday materials.
Yeah, that's a good way to put it. Materials have these wild, distinct characters in how they respond to heat. But to get to those personalities, we first have to shrink down to the microscopic level.
Because in everyday conversation, we just toss around the words temperature and heat like they're synonyms. Like, I
Mhm.
turn up the heat, the temperature goes up. Same thing, right?
Well, no. In physics, treating them as the same thing will just completely derail your understanding. The manual grounds us immediately in what's called the kinetic molecular theory.
Right. Which sounds complicated, but it's really just about motion.
Exactly. Every substance you interact with, so solid block of steel, a glass of tap water, or the oxygen currently filling your lungs, it's all made up of vibrating, moving molecules.
Just constantly buzzing around.
Yes. And temperature is nothing more than a measurement of the average kinetic energy of those moving molecules.
Okay, so let's unpack this. If those microscopic molecules were cars on a highway, temperature is basically just the radar gun.
That's a great analogy.
Yeah. It's the speedometer telling us the average speed of traffic. Higher
Yeah.
temperature simply means faster molecules.
Right. Temperature is just the state of the material. But heat is entirely different. Heat is an action. It's the actual transfer of energy from one object to another due to a difference in temperature between them.
Okay, so if temperature is the radar gun, heat is the actual gasoline being pumped into the system to force those cars to accelerate.
Exactly. The gasoline is the energy, and the speed of the cars is the result. And because heat is a form of physical energy, it isn't actually measured in degrees.
Wait, really?
Yeah, it's measured in standard energy units. So you'll see things like joules, kilojoules, or in the imperial system, the British thermal unit, the BTU.
Oh, right. Like when you buy a window AC unit and it says that's 10,000 BTUs, that's measuring the actual energy transfer, not the temperature itself.
Exactly. What's fascinating here is that understanding that distinction reveals how the radar gun, the temperature, strictly dictates the fundamental rules of the road. Well, temperature strictly dictates the direction of heat transfer. Objects with more internal energy always transfer heat to objects with less internal energy. Spontaneously, anyway.
So a cold object doesn't pass its coldness to a hot object.
Right. Cold doesn't technically exist as an active force. It's just a lack of heat. The hot object is simply bleeding its energy into the cold one until their molecular speedometers balance out.
Okay, that makes so much sense. But that brings us right back to Daniel Fahrenheit and his salty bucket of ice.
It does.
Because if temperature is just molecular speed, humanity eventually had to figure out a way to put numbers on that radar gun. And the numbers we use every day have a remarkably messy history.
They really do. The manual breaks down the major scales used in industrial trades. In the U.S., obviously, the Fahrenheit scale dominates. We measure the 0 point, which happens to be negative 17.77 degrees Celsius.
Which is just such a random starting line.
It is. And from that arbitrary starting line, Fahrenheit determined that pure water freezes at 32 degrees and boils at 212 degrees. That leaves exactly 180 scale units between freezing and boiling water.
Which feels incredibly chaotic when you put it next to the Celsius scale. I mean, Anders Celsius takes his thermometer, puts it in pure freezing water, and says, let's call this 0.
Nice and clean.
Right. And then he moves it to boiling water and says, let's call this 100, a perfectly clean 100 steps between freezing and boiling.
But because both of these guys just pick random phenomena in nature to be their 0 points, we end up with this bizarre mathematical quirk where the two scales intersect.
Oh, right, the magic intersection.
Yeah, they cross over because a Fahrenheit degree represents a physically smaller change in temperature than a Celsius degree. You have 180 steps to get from freezing to boiling in Fahrenheit, but only 100 steps in Celsius.
So Celsius steps are bigger.
Exactly. And because of that different slope, negative 40 degrees Celsius is exactly equal to negative 40 degrees Fahrenheit.
Honestly, definitely keep that in your back pocket for trivia night. But calling both of those 0 points arbitrary implies that a real non-arbitrary 0 actually exists somewhere, right?
It has to exist. If we connect this to the bigger picture, if temperature is purely the measurement of molecular motion, there has to be a physical bottom.
Like you can't have negative kinetic energy.
Right. You can't go slower than stopped. There's a point where the cars on the highway turn off their engines, put it in park, and completely stop moving. 0 kinetic energy.
Absolute 0.
Exactly. Absolute 0, which sits at negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. And to handle this, scientists developed absolute temperature scales.
Because the math gets weird otherwise.
It completely breaks. The Kelvin scale uses Celsius-sized degrees, and the Rankine scale uses Fahrenheit-sized degrees. But on both of these, 0 literally means 0 motion.
I always pictured absolute 0 as just a giant, perfectly still block of ice. Like, things just get infinitely hard and frozen. But why do engineers or instrument technicians actually need an absolute scale for their day-to-day math?
It's a fair question. Why isn't Celsius good enough to build a boiler, right?
Yeah.
Well, think about gases rather than blocks of ice. The laws of thermodynamics dictate that the pressure and volume of a gas are directly proportional to its temperature.
Okay, so if you heat a balloon, it expands. If you cool it down, it shrinks.
Exactly. When engineers are calculating the complex dynamics of gases under extreme pressure, they use formulas that multiply or divide by the temperature. If you plug a negative Celsius temperature into one of those equations, the math breaks.
Wait, how?
It will spit out an answer claiming the gas has negative volume.
Oh, which would mean the balloon takes up less than 0 space. It like folds inside out into another dimension.
Right, which is a physical impossibility. Absolute 0 gives us a true baseline where matter literally cannot get any colder, ensuring all that thermodynamic math stays positive and reflects physical reality.
That makes perfect sense. But, the manual points out another math trap that catches people constantly when we talk about scales.
Oh, the temperature shift trap.
Yes. Calculating a specific temperature point is completely different from calculating a temperature shift.
It all comes back to those offset starting lines we talked about. You want to convert a specific reading, say a thermometer says 25 degrees Celsius, you multiply by the ratio of the scales, which is 9/5, and then you have to add 32.
Because Celsius starts at 0 for freezing, while Fahrenheit starts at 32.
Exactly. You have to bridge that gap.
But if the weather reporter says the temperature outside is going to drop by 10 degrees Celsius overnight, you don't use that formula.
No, you don't.
Because it doesn't matter if the temperature dropped from 30 to 20 or from -5 to -15. The change is just 10 units.
Right. And since every 1 Celsius degree covers the same physical distance as 1.8 Fahrenheit degrees, a 10 degrees Celsius drop is simply an 18 degrees Fahrenheit drop. No adding 32.
You just multiply the drop by 1.8. It's so simple when you lay it out like that. But the really fascinating part to me is that a 10-degree temperature shift doesn't impact every material the same way.
Not at all.
Like, even if we perfectly measure the energy being transferred, materials do not react to that heat equally.
This is where those material personalities come in that we mentioned earlier. The manual introduces this concept called specific heat capacity.
Which is basically a measurement of how stubborn a material is when you try to heat it up.
That's exactly it. It's the amount of heat required to change the temperature of 1 unit of mass by 1 degree. Let's compare a chunk of copper to a glass of water.
Okay.
To raise the temperature of a kilogram of copper by 1 degree, it takes a very small amount of energy. The internal structure of copper is highly conductive.
Right. It absorbs the energy, the molecules immediately vibrate faster, and the temperature just spikes.
Yep. But water, on the other hand, is incredibly stubborn. It takes roughly 11 times more heat energy to raise the temperature of water than it does for copper.
That is wild.
It is. You can pump massive amounts of gasoline into the water system, coming back to your analogy,
Yeah.
and those cars just refuse to accelerate.
So why is water so stubborn? Why does it ignore the gasoline?
It comes down to the shape of the molecule. Water molecules have strong hydrogen bonds connecting them to each other. Think of those bonds as microscopic, heavy-duty shock absorbers.
Oh, I like that.
When you pump heat energy into the water, those shock absorbers stretch and absorb a massive amount of the energy before the actual molecule itself starts moving any faster.
So the energy is captured in the structure rather than translating into straight line speed.
Exactly.
But the manual throws a massive curveball here. The actual physical state of the material changes its personality completely.
Yes, it does.
Like solid ice, which is literally just frozen water, only requires about half the heat to raise its temperature compared to liquid water.
Mhm.
Same H2O molecules, completely different specific heat. That feels like a glitch in the physics matrix.
It really does seem like a glitch, but think about what happens to those shock absorbers when water freezes. In ice, the water molecules are locked into a rigid, crystalline structure. They are tightly bound. So when you add heat, they can't do much else but vibrate in place, so the temperature goes up relatively quickly. But in liquid water, the molecules are loose. They're tumbling, rotating, swaying, interacting dynamically.
So when you add heat to liquid water, the energy gets hidden in all those extra dance moves.
Dance moves, I like that.
Yeah. The molecules start spinning and tumbling, absorbing the energy in all these different directions, which means less energy is going toward the straight line speed that our thermometer actually measures.
That's a brilliant way to conceptualize it. The energy is dispersed into the tumbling. And this raises an important question. Think about what this means for the environment around us, or industrial processes.
Because water is such an incredible thermal sponge.
Exactly. It can absorb a massive amount of heat without its temperature spiking dangerously high. That is why engineers use water as the ultimate thermal transport mechanism in industrial cooling systems, or like nuclear reactors.
Wow, right.
It's also why coastal cities have milder climates. The ocean absorbs the brutal summer heat without boiling and slowly releases it during the winter.
Okay, so we know liquid water acts like this heat sponge and solid ice heats up twice as fast. But what happens at the exact boundary line?
You mean the phase change?
Yeah, like when ice hits 0 degrees Celsius and begins to melt, or when liquid water hits 100 degrees and actually begins to boil.
That boundary line introduces the difference between sensible heat and latent heat. Everything we've discussed so far, adding heat and watching the thermometer rise, is sensible heat. You can literally sense the change in kinetic energy on an instrument.
But then you hit a phase change plateau. Let me make sure I've got this right. Let's use a pot of boiling water. I have a pot of water on the stove. The thermometer hits 100 degrees Celsius, the boiling point.
Oh.
If I take an industrial blowtorch and just blast the side of that pot with maximum heat, the liquid water itself doesn't reach 105 or 110 degrees. The extra heat just makes it turn into steam faster.
That's exactly right. The liquid water refuses to get hotter. The thermometer stays dead flat at 100 degrees Celsius. The extra heat you're pumping in is no longer sensible. It becomes what we call the latent heat of vaporization.
But wait, where's all that blowtorch energy going if it isn't making the molecules move faster?
It's being consumed to literally break the physical bonds keeping the molecules close together. To move from a liquid state to a gas state, the molecules have to be ripped apart from each other.
Ugh. So they're trapped in a crowded room, bumping shoulders. And the energy from the blowtorch is being used to smash the walls down so those molecules can fly out and bounce freely through the entire building as steam.
Smashing those walls takes a tremendous amount of force. The energy doesn't increase their speed, it changes their physical state. Once a molecule breaks free and becomes steam, then, and only then, if you keep heating that isolated steam, its temperature will rise again.
But during the transition, the temperature is totally locked.
Completely locked. And the exact same process happens when ice melts. It's called the latent heat of fusion. A glass of ice water will sit at exactly 0 degrees Celsius until the very last sliver of ice has melted into liquid.
That's wild. You can pump near infinite heat into boiling water, and it stubbornly refuses to get hotter until it's entirely steam.
Yep.
That invisible rule governs so much of our cooking and engineering.
Mm.
But what happens physically to an object when it absorbs heat, but it hasn't reached its melting or boiling point yet?
Well, the energy still has to do something to the material, even if it doesn't change state. And this brings us to the laws governing mechanical work and thermal expansion.
Right, the first law of thermodynamics.
Exactly. The first law establishes that energy isn't created or destroyed, it is only transformed. The internal energy of any system is a combination of the heat it receives and the mechanical work done on it.
So if I drag a heavy wooden crate across a concrete floor, I'm doing mechanical work. The friction between the crate and the concrete creates heat.
Yes.
So the biological energy of my muscles transformed into kinetic movement and then directly into heat energy, which is warming up the floorboards.
Spot on. Now, when the solid floorboards, or any solid material for that matter, absorb that heat, the molecules vibrate faster. As they vibrate more violently, they naturally push slightly further apart from their neighbors.
Because they need more room to bounce around.
Exactly. And this results in linear expansion. The object literally gets larger. And because materials have personalities, like we said, they expand at different rates, which engineers measure with a coefficient of linear expansion.
Right. The manual actually provides tables of these coefficients. Aluminum, for instance, expands significantly more than steel when exposed to the exact same temperature shift.
It does.
And engineers use that discrepancy brilliantly in thermostats by creating what's called a bimetal strip. They take a thin strip of steel and a thin strip of brass, and they permanently weld them together face to face into one solid piece.
Right, because brass has a higher coefficient of expansion than steel. When the room warms up and that joined strip absorbs heat, the brass physically tries to grow longer than the steel it's glued to.
But because they're fused together, the strip can't expand in a straight line. The growing brass forces the entire strip to bend into a curve. It's like a microscopic three-legged race. If you tie two runners together at the ankle and the runner on the left naturally sprints much faster than the runner on the right, they aren't going to run straight down the track.
No, they'll veer off.
The faster runner is going to pull the slower one into a sharp curve. That bending motion is exactly how a mechanical thermostat works. The room cools down, the metals contract at different rates, the strip bends backward, and physically touches a contact to complete an electrical circuit, turning your heater on.
It is an incredibly elegant use of thermodynamics.
Mm.
But, expansion isn't just linear, it affects area and volume as well. And area expansion has a quirk that trips up almost everyone.
Oh yeah, the hole in the plate thing.
Yeah. Imagine a flat metal square plate and someone has drilled a perfectly circular hole right in the middle of it. If you throw that plate into an oven and heat it up, what happens to the size of the hole?
I mean, my immediate instinct before reading the source material was that the metal expands into the empty space. Like it puffs up, making the hole shrink.
Most people assume the expanding metal fills the void, but in reality, the hole expands outward. It gets larger.
That is so counterintuitive.
It is, until you picture this specific ring of metal atoms forming the very edge of that hole. As those atoms heat up, they vibrate and push away from each other. For the atoms in that circle to get further apart from one another, the circumference of the circle has to increase.
Oh, so the entire object, the hole included, scales up proportionally.
Exactly, like zooming in on a digital photograph.
It's just another one of those hidden rules dictating reality. We've seen how mechanical work turns into heat via friction and how heat physically expands materials, but can we reverse the process?
What do you mean?
Like, can we take heat and turn it perfectly back into mechanical work?
That is the ultimate test of the second law of thermodynamics. And the answer provides a pretty harsh reality check for every engineer on Earth.
Oh.
Yeah, the second law dictates that mechanical work can turn into heat with 100% efficiency. Your crate dragging on the floor perfectly converted work into friction and heat. But turning heat back into mechanical work, what we call a heat engine, like a steam turbine or the combustion engine in your car, is never 100% efficient.
Wait, so it's a completely one-way street?
The universe enforces a strict one-way toll. What's fascinating here is that a heat engine requires a high-temperature source to provide the heat and a lower-temperature sink to receive the exhaust. During that flow from hot to cold, we siphon off some of the energy to turn a turbine or push a piston.
Okay.
But some heat is inevitably permanently lost to the environment. You can never, ever capture all of it.
Wow. Let's just retrace the massive journey we've taken today. We fundamentally redefined how we look at hot and cold visualizing temperature as the speedometer of microscopic molecular traffic, and heat as the actual fuel driving it.
Mm-hmm.
We untangled the messy history of Fahrenheit's salty ice bucket and why absolute zero is required to keep the math of the universe from breaking down into negative space. We exposed the stubborn, specific heat of water, hiding energy in its molecular dance moves, and the bizarre flatline plateau of latent heat, where boiling water refuses to get hotter until it rips its molecules into steam. And finally, we looked at the physical consequences. The three-legged race of a bimetal strip bending in your thermostat and the strict, inescapable rules of thermodynamics.
If there is one concept from this manual that should fundamentally change how you view the world, it's the profound implication of that second law of thermodynamics.
How so?
Consider this. If mechanical work can become heat perfectly, but a heat engine can never turn heat back into work perfectly, it means every single machine humanity ever builds is locked in a slow, losing battle.
Oh, wow.
Every engine cycle, every turning gear, every mechanical action leaves behind a tiny bit of unusable, leftover heat dispersed into the universe. Next time you place your hand on the hood of your car after a long drive, realize that you aren't just feeling a warm block of metal. You are feeling the permanent, irreversible toll of the second law of thermodynamics playing out in real time, right under your palm.
That is a staggering thought to leave on. Thank you for joining us on this deep dive.